Hi, everyone.
Hi, thanks for coming.
Thank you. Thanks for the opportunity to talk.
Yeah, so Sherlock has had a long career in geospatial and has always managed to remain at the cutting edge, I've noticed. So I'm not surprised to learn he's already been delving into the world of geospatial embeddings and figuring out how to use PGVector and Postgres and PostGIS with them. I'll turn it over to you, Shoaib, and take over the screen share and tell your story
Okay.
and see it.
Can you all? Okay, awesome. Let me just get this play button. All right, everyone. I see. Yeah, it's really an opportunity a privilege to be able to talk to you all, and thanks for this opportunity. I'm going to be talking about geospatial embeddings, and in particular in the context of PostGIS and a particular extension called PGVector. And the work that we've been doing in using it in the latest project I've been working on called Geobase, and some of the lessons we learned, and some of the pain points, and some of the future developments that we see coming in order to make it even more useful. Just a little bit about me. I'm Shoaib. I've been around the geospatial and open source community for a long time, and like many of us here, I have Postgres and PostGIS to thank for paying my bills. My current project is a backend as a service called Geobase, and it's essentially a batteries included backend as a service for geospatial developers. And one of the things we try to do there is make sure that it's built on Postgres, and we try to make sure that it's really has all the best geospatial extensions that are available out there. So recently we added A5, which is a discrete global grid, into it, and we made the Postgres extension for that. It also has vector tile server built on PG tile serve, and a raster tile server as well. And it has like data importers and connectors and so on. So that's what I'm working on these days. And let me now turn to why are we talking about this? So we are seeing obviously a lot of people are building these AI bots and AI assistants, and the fundamental architectural block in that is the embedding database, and that's used for something called retrieval augmented generation, RAG, and you would have seen that word thrown around a lot. That's how most chatbots are built. And it's also used in similarity searches, finding similar objects in an image database or even text, as well as some downstream training tasks. So you can store embeddings during some kind of a preliminary training step, and then use those embeddings later in order to do few shot training or even fine tuning based on those embeddings for more specific tasks. So we might have buildings based model, and then you might take the embeddings from that, and then take some of those embeddings to train a building model for detecting damaged buildings or diseased crops and so on. So essentially, the applications of embeddings are many in terms of their usage or the tasks they can perform. Things like classification, retrieval, uh, um, PCA, detection, segmentation, and depth detection. Now, let me give you a few sort of examples of how we use it. So this is an image taken by drone by the humanitarian OpenStreetMap and the community in Freetown in Senegal. And here we're detecting dumping grounds for trash, and as well as like any other features that they're interested in. Here I'm detecting trees simply by drawing and doing a similarity search. And all of this is powered by Postgres and PostGIS and PGVector. So I'll get in more into how we build something like this. So the fundamental building block of a vector database is obviously the vectors themselves, the multidimensional numerical vectors, but then the index that is used to do the search. And the most common way this is done is by using something called hierarchical navigable small worlds. It's a bit of a mouthful for basically a graph that is multi-resolution, and then you do a search using a graph traversal to find the nearest neighbor to your query. So here, in this example, this image, hopefully you can see my mouse, uh, is the query vector, and we find the closest matching vector in it, and then we find the closest matching in the next level, and then until we get to the highest resolution to find the matching, the closest matching vector to our query. Now, you can also think of it this as in a 2D scenario, and we'll get into why this is important, but there are 2D embedding indices as well, vector indices as well. And it's important to know that there's an entry point when you're starting the search, and how you get to that entry point is super important. Okay, so what does it look like in code? So creating a table with, after you create your extension, your classic create extension, PGVector. After that, you create your table. And here I'm creating a table with a vector column and providing it the dimensions of my vector. Now, this is dependent on your model. So if your model is going to produce a certain type of, a certain set of embeddings or dimension of embeddings, you need to create a table for that model. There's no point creating a table with different model outputs because you just can't compare those. And this is how you create an index, right? So this is the HNSW index that I mentioned earlier with a cosine similarity operator or cosine distance operator next to it. And once you're done with that, you can do your query. Now, all is well here, except we have a bit of a problem. And the problem here is that I have a where clause here. And if I remove that where clause, everything will be fine. But if I have a where clause, the Postgres query planner does not know how to use, basically it doesn't play well with vector indices. The query planner is still not well integrated with query or nearest neighbor searches, basically. And this query will result, it may result in actually our output being fewer than 10, even though we've asked for 10 particular results. The reason being that this where clause will be applied post filter, post embedding filter. So it goes off and does a search, finds say 10 nearest neighbors, and then does it apply this vector, this category, and is assuming there's only 5 electronic records, it'll have, or even make in this subset of that it found, it will only show 5, even though it could have kept searching. If it knew about that post filter, it could have searched more and found more records. Now, in the newest version of PGVector, they do solve this, but it's not really an elegant solution. Though this is called a recurrent or reapplication of the search. If it's called a sort of it basically iterates on the query. Once it sees that its results are fewer than what it expected. So we get to this problem of the trade-off, the recall trade-off versus the latency trade-off, and yeah, it's a tough one. it's one of the biggest challenges we have right now in the vector database space. It's not just for Postgres. Most vector databases have to their users have to deal with it, or their DB or their administrators have to deal with this. Now, there is a new solution right now that just came out recently called PGVector Scale. And PGVector Scale is it's not a competitor to PGVector. It's essentially an extension to the extension. And the only reason it's an extension and not part of PGVector Scale is because it's written in Rust, and PGVector was written in C. And just because of pragmatism, they wrote it in, they just released a separate extension. But it depends on PGVector. And all it does is adds a new type of index to solve that that sort of post filtering problem. The way this works is that when you want to do something that has a secondary filter, you have to, well, it provides you a composite with a composite index. And that is called disk ANN, or more precisely, it's called streaming disk ANN. And it's based on a paper from Microsoft, which tries to improve the memory performance on very large vector databases. In addition, it allows for composite indices. And in this case, I'm creating a composite index with the label. And the label is a small int array. And the idea here is that you store your labels in a lookup table and add those to your array as you need them. And then when you do this query, it is way faster, right? It will guarantee the 10 results that we want and you know solve that problem for us. So you're all probably wondering, well, we all came here for geospatial embeddings, so I don't want to learn about graph theory. So let me move on to geospatial embeddings. And how do you get geospatial embeddings, right? Like we've talked about embeddings abstractly, but what about geospatial embeddings? So here I'm showing some the bounding boxes, and each of these bounding boxes is a patch that is produced by running an AI model, such as a vision model, such as a vision transformer model. In this case, it's the Dino version 3 from Facebook. And it produces for each of those patches a embedding that represents the sort of the high level multidimensional features representing that image, that part of the image, right? And that's a function of how it was trained. So a lot of these bigger models are trained on so many data sets that once you apply them to geospatial use cases, it starts to distinguish things, not necessarily in what those things are, but it does start to distinguish things. So in this case, what I showed here is in addition to distinguishing the features, I'm also here. You can see I'm selecting the label buildings. So this is a process model, which is taking those embeddings and applying a secondary label to it. And I can see that from I see that here. And this is this sort of Dino vision transformer model, as well as a grounded Dino model. Now you might think, okay, all this all solved, everything is good. But unfortunately, the geospatial filters suffer from the same problem that I described earlier with the filters on particular where clauses. And so there is no way for the query planner to be able to know which query it should prioritize, which where clause which filter it should prioritize, and we have the same problem of inefficient queries or poor recall. And sometimes, if you run the spatial filter first, then the vector index is not even used. And we have been running some tests. I'm just going to be going over some of the benchmarks that we've been doing. So you get a bit of an insight into what is going on here. So this is some of the data that we ran the benchmarks on. We have sort of these data set of point geometries, and then we have bounding boxes that we use for different benchmarks. So we have different size bounding boxes for different selectivity and cardinality, so that we can test different scenarios. So just to tell you what the hardware setup was, or the benchmark setup was, we had 100,000 geometries. We have the GIST index on PostGIS, HNSW index on vectors, and then it's just a small 2 CPU, 4 GB RAM droplet in DigitalOcean, and the default Postgres configuration. We had some baseline queries with filters, spatial, vector, and nose sequential scans. And then we have our test queries, high selectivity, sort of moderate selectivity, low end selectivity. And then we have some CT versions of the same queries. And I won't get into the sort of the guts of this, but the main point I want to get across is that we still have the same problem that we had when I was describing the non-spatial filters. And we have some of these queries are running for 10 seconds, and they're not using the vector index. And this is the query number 3, which ran for 1.5 seconds. This is my selectivity area. Even though it's a small area, the vector search had to search for the whole space. And not only that, when you do this query, the where clause causes the query planner to lose the embeddings lose their ability to do the actual graph traversal, because you've done a subselect, or you've done a where filter. So this is results from that. The vector index was not used, and even though we only had 633 actual records that were going to be selected by the spatial selection, that's really inefficient, right? Even worse is query 5, where we had 10 seconds of runtime, and even though it's just 5% of the data set with 5,000 records. Spatial query number 7 was a bit of an anomaly. What happened here is that it ran quite quickly, but it was because the query was actually using a heap scan. In other words, the data had gotten cached, and so there was a bit of an anomaly there. But the problem persists. We can do our queries and use our indices individually, but when we combine them, we get very slow queries. And we really, we don't have a solution for this. And this is something we've been sort of thinking about for the last few months. And this is something really a call to action as well, and so sort of seeking collaborations on this. But we'll be sharing some code later on with some ideas around trying to create a composite index for geospatial and vector embeddings. So the idea would be something like this, where you have a composite index, very similar to the way we saw the labels, the array, the integer array, and that can allow us to do much more efficient lookups. And the initial idea is something like being able to do some pruning of the graph before we start doing the traversal, by storing at each node a geometry in a key, something like a bounding box. and maintaining a graph search structure so that we can, as we're doing inserts or deletes, maintaining that graph structure to be able to search. So it might look something like this, where you have your query with both vector and geometry, and you have sort of a high-level coarse grid, which does a pre-select to find entry points into your graph, and then we do a graph traversal with the um, with the geometry key that's stored in each node, and then the final result. Okay, that basically concludes my talk. If people are interested, I can show a little bit of what sort of how we interact with embeddings and uh, and some of the other sort of yeah, or we can go jump to questions.
Well, let's see this embeddings demo.
Okay. So this is a GeoJIGS, which is a JavaScript project, open source. It allows you to do uh, embeddings, look up or run an embedding model within the browser. So it's really using something called Transformer.js, which runs the embeddings using your laptop's GPU. So I draw here, um, and I can say extract. It will take this image in what I'm looking at, grab the Mercator tile, and then just show me the embeddings.
Those things which are similar.
Yeah, so yeah, and I just have a little JavaScript code that basically says, when I hover, show me the closest embeddings. I'll just highlight them with different
Right.
colors.
So you hover over the roads
Uh,
and you see the roads light up. You hover over the trees and we see trees light up. Now you hover
exactly.
over the roads, but the roads are lighting up a lot near your hover and less further from your hover, even though they're like still roads. Is this like, is this an effect? Like I was going to
Yeah,
ask
yeah,
about the whole getting
yeah.
geospatial indexes merged with embedding indexes and wondering if like it feels duplicative for like a geospatial embedding because surely part of the geospatial embedding is where the thing is. Um,
Right. It, it, um, I mean, if you, yeah, I think that the way you think about the embeddings is not necessarily. Um, I think the use case would be basically the downstream applications of embeddings rather than. Um, is that sorry? I don't think I fully understood your question. Is that what you're
oh, well,
asking?
I mean, we're kind of seeing it in your example here. Is just like these vectors
But
not only know a whole bunch of things about the underlying characterizations at the place they are, they also know where they are, presumably, and they know who their neighbors are and the characterizations of their neighbors. Um,
yes,
So given that they know where they are, there's like a hardcore sort of spatial filter should be
I think what they
extractable. I
know
guess the
is
trick is you don't know
basically
which
the
dimensions.
similarity.
Yeah. I had another question
Um,
just about the embeddings in general, like from a practical point of view, someone who wants to play with this, like what models are you using to get embeddings from?
yes.
What model can I like
So
hand the
the
lat
most
long and get an
common
embedding
ones
vector back
are
for?
um, things like the Dino version 3, which is just actually one of the most they're sort of off-the-shelf models.
Okay.
And then there are, of course, the very large models, which are much more costly to run. Um, and those are things like the foundation models that things like Clay or the ones from Microsoft. The name I forget the names right now, but they're the sort of the really large models, and
Yeah.
uh, and then the ones from Google, which is the um, uh, Alpha Earth. Even though that model is currently not really implemented, it's just the embeddings are available.
Right. And what kind of posting level are those embeddings distributed?
Sorry, what
Resolution?
kind of?
What resolution?
I think the alpha, I don't think I remember exactly, but it's some, I think it's like uh, zero point 0.2 degrees,
Hmm.
but don't quote me on that. But
Yeah, yeah,
they're
yeah.
quite coarse. I think they come out to be around um, a kilometer, but maybe somebody else knows that better.
Yeah. Questions from the chat. Do you need to have a GPU to run this software, or can it work with ordinary CPUs?
So this one will work on an ordinary CPU as well. This model is small enough to. So some of these models, like this one, is quantized and will run on. Um, but there are other models like the I think yeah. So the some of these clip models, they're much
Hmm.
bigger and they require GPUs. So this is actually um, a feature in Geobase where you can actually put in your geotiff and select your compute based on what you're doing. And some of these do require GPUs. Um, yeah.
And and another question, are you using PGVector successfully for doing geospatial embedding work? It sounds like there's lots of problems with it, so should it best be avoided? Are there alternative tools that can do this better?
No, no, I don't think it should be avoided. In fact, it should be embraced because the alternatives are these either proprietary databases, right, the proprietary ones, or the open source ones, which are again like they have either um, they hide a lot of the complexity. And I think that the power of PG Vector is that actually gives you much more ability to control what you can query and performance. So, for example, you can actually fine tune it to say in my nearest neighbor search, select in my traversal. You can actually tell it, okay, look for up to 40 nearest neighbors. And then depending on your workload or your type of your data, you can get it to perform the way you want. The problems that I described are problems that are happening across this vector embedding vector database space. It's not unique to PG Vector. Um, so you will find this people are collaborating on research in this. It's a heavily researched and it's an academic topic as well.
Yeah, awesome. Question from Charles Gauvin. I was wondering if you had to do any pre-training for the Dynov 3 model, or you're simply using the weights provided by Meta. Your urban seams seem rather
It's
different from the
the
overall distribution used to train the model.
Yes. So it's the original meta model, and then it's been quantized by the Onyx community, the Onyx open source Onyx community. So it's not the original model per se. We could run the original model, but then for that you would need the GPU, right? But the one that I just showed with the one in the browser, it's uh, it's been it's been compressed using a technique called quantization, where you reduce the precision of your embeddings and makes the model smaller. But it still performs incredibly well.
Awesome. Well, thank you so much for coming and sharing this with us, Shoaib.
Thank you.
It's great to see you and keep up the good work.
Nice to you
I
too.
love seeing your forays into the cutting edge of geospatial. Um,
Thank you very much. Thanks for the questions.